Welcome to DAR Tutors for online and home tuition. Today, we will begin our study of eigenvalues and eigenvectors, which are fundamental concepts in linear algebra and are directly relevant to the IB Mathematics Applications and Interpretation Higher Level curriculum. We will be covering a range of topics from this chapter. By the end of this video, you will be able to First, you'll be able to define eigenvalues and eigenvectors. Second, you'll learn how to find the eigenvalues of a square matrix. Third, you will be able to determine the eigenvectors that correspond to those eigenvalues. Fourth, you'll understand the process of matrix diagonalization. And finally, you will learn how to use diagonalization to calculate powers of a matrix efficiently. We will then apply these methods to solve 5 IB-style practice questions. Let's start with a classic problem that demonstrates the utility of these concepts. The weather model. Imagine a seaside town in springtime. Observations show that each day the weather is either sunny or rainy. Crucially, tomorrow's weather depends only on today's weather. This is the hallmark of a Markov process. If it's sunny today, the probability of it being sunny tomorrow is 0.8. So it's 80% likely to stay sunny. And if it's rainy today, the probability of it being rainy tomorrow is 0.4, a 40% chance of staying rainy. We can represent these probabilities in a matrix called the transition matrix, denoted as T. The columns represent today's state, and the rows represent tomorrow's state. So the first row is for sunny tomorrow, the second for rainy tomorrow. The first column is for sunny today, the second for rainy today. Plugging in our probabilities, we get this matrix. Notice that each column sums to 1. For example, if it's sunny today, the probability of it being sunny or rainy tomorrow must add up to 100%. Now let's consider the meaning of the entries in this transition matrix. What does the term T12 equals 0.6 represent? Remember, the first subscript is tomorrow's state, and the second is today's. So T12 is the probability of the weather being sunny tomorrow given that it is rainy today. This is the value that was not explicitly given but must be derived. Next, we can define the state of the weather using a state matrix, S. A state matrix is a column vector where the first component is the probability of the weather being sunny, and the second is the probability of it being rainy. Suppose it is sunny today. We can represent the initial state, S0, as the probability of sunny is 1, and the probability of rainy is 0. This means we are certain the weather is sunny to start. To find the state matrix for tomorrow, S1, we simply multiply the transition matrix T by the current state matrix S0. So S1 equals T times S0. Performing the matrix multiplication, we get the state matrix S1. So what does this matrix S1 mean? It means that tomorrow, the probability of it being sunny is 0.8, or 80%, and the probability of it being rainy is 0.2, or 20%. This makes sense, as the problem states if it's sunny today, it's 80% likely to be sunny tomorrow. Now for the central question. What happens in the long term? Will the probabilities of sunny and rainy days stabilize? The problem asks if there is a special state matrix, let's call it S infinity, such that applying the transition matrix T to it doesn't change it. That is, T times S infinity equals S infinity. This special matrix S infinity represents the long-term stable distribution of sunny and rainy days. It's the state the system will eventually settle into. We call this the steady state. Our goal in this chapter is to develop the tools to find this steady state. This involves understanding eigenvalues and eigenvectors, which are properties of the matrix T that describe its long-term behavior. By finding these, we can predict the weather in the town, not just tomorrow, but weeks or even years into the future. Now let's formally define our central concepts. Eigenvalues and eigenvectors. These are properties of square matrices that reveal a lot about how they behave. Let A be a square matrix. If we can find a non-zero column vector x and a constant or scalar lambda, such that A times x equals lambda times x, then we have found an eigenvector and its corresponding eigenvalue. Let's rephrase this. When we multiply a matrix A by a vector x, we are performing a transformation. Normally, the resulting vector x points in a completely different direction than x. An eigenvector x is special because the transformed vector x is parallel to x. The only change is the length or scale, which is given by the eigenvalue lambda. So, an eigenvector is a direction in space that is preserved under the transformation, and the eigenvalue tells us the scaling factor along that direction. In our weather model example, the steady state S infinity is an eigenvector of the transition matrix T, and its corresponding eigenvalue is 1. This means the state is unchanged after applying the transition. Our first task is to find these eigenvalues and eigenvectors for a given matrix. We will now focus on our first objective, finding eigenvalues. Let's start with our defining equation. X equals lambda x. Our goal is to solve for the scalar lambda. To do this, we first need to rearrange the equation. Subtract lambda x from both sides to set the equation to 0. The next step is crucial. We cannot simply factor out x because A is a matrix and lambda is a scalar. We need to introduce the identity matrix I. Since the identity matrix times x is just x, we can rewrite lambda x as lambda ix. This allows us to factor out the vector x. Factoring out x gives us the matrix equation. The quantity lambda I minus a all multiplied by x equals the 0 vector. We'll call this equation star. For this equation to have a non-zero solution x, the matrix lambda y minus a must be singular. This means its determinant must be 0. If the determinant were not 0, the only solution would be x equals the 0 vector, which we have excluded by definition of an eigenvector. This gives us our characteristic equation. The determinant of lambda I minus a equals 0. Solving this polynomial equation for lambda will give us the eigenvalues. This polynomial dt I lambda I minus a is called the characteristic polynomial. Let's work through an example to see how this is done in practice. Consider the matrix A equals 0, -3, -4, -1. First, we set up the characteristic equation. We need to calculate the determinant of lambda I minus a. This simplifies to the determinant of the matrix, lambda 3, 4, lambda plus 1. The determinant of a 2 by 2 matrix is the product of the main diagonal elements minus the product of the off-diagonal elements. This gives us lambda times lambda plus 1 minus 12. Expanding and simplifying gives us the characteristic polynomial. P of lambda equals lambda squared plus lambda minus 12. Now we need to solve the characteristic equation by setting this polynomial to 0. Lambda squared plus lambda minus 12 equals 0. This is a simple quadratic equation. We can factor it into lambda minus 3 times lambda plus 4 equals 0. This yields two distinct solutions for lambda. Therefore, the eigenvalues of the matrix A are 3 and 4. These are the two special scaling factors for this matrix. So we have now achieved our first objective. By solving the characteristic equation, we can successfully find the eigenvalues of a matrix. Eigenvalues can come in different forms. Let's look at a case where the characteristic equation has a single repeated root. Consider the matrix A equals -3, -1, 1, -1. First, we set up and solve the characteristic equation det lambda y minus a equals 0. Calculating the determinant gives us lambda plus 3 times lambda plus 1 minus -1, which equals 0. Expanding and simplifying, we get lambda squared plus 4 lambda plus 4 equals 0. We can recognize this as a perfect square. Lambda plus 2 squared equals 0. This equation has only one distinct solution. Lambda equals -2. We say that -2 is an eigenvalue with an algebraic multiplicity of 2. Let's also look at a case with complex eigenvalues, which will be important later when we discuss eigenvectors. Consider the matrix A equals 2, 5, -1, 0. Again, we start with the characteristic equation. This is the determinant of lambda I minus a equals 0. Calculating the determinant gives us lambda times lambda minus 2 minus -5 equals 0. This simplifies to the quadratic equation lambda squared minus 2 lambda plus 5 equals 0. This quadratic equation does not factor easily, so we use the quadratic formula. The quadratic formula gives us lambda equals 2 plus or minus the square root of 4 minus 20, all divided by 2. This simplifies to 2 plus or minus the square root of -16, divided by 2. The square root of -16 is 4i, so the eigenvalues are 1 plus 2i and 1 minus 2i. Notice they are a complex conjugate pair, which is always the case for real matrices. We have now seen real and repeated, real and distinct, and complex eigenvalues. We have reached the 10-minute mark. If you are finding this tutorial helpful and would like to explore this topic or any other in greater depth, I invite you to contact DAR Tutors. We offer expert online and home tuition in the IB, A-Level, and IGCSE curricula. Whether you need help with a specific concept, exam preparation, or general academic support, our qualified tutors are here to guide you. Visit dartutors.com or use the contact information provided to schedule a free consultation. Now that we know how to find eigenvalues, let's move on to our next objective, finding the corresponding eigenvectors. Once we have found an eigenvalue, say lambda naught, we substitute it back into the eigenvector equation, which was star. This gives us a system of linear equations that we need to solve for the components of the eigenvector x. It's important to remember that since we set the determinant to 0, the matrix lambda naught I minus a is singular. This means the system of equations will have infinitely many solutions. These infinitely many solutions are all scalar multiples of each other, forming a direction. Any of these non-zero scalar multiples can be chosen as the eigenvector. Let's revisit the matrix A from our first example. First, we need to find the eigenvalues. Setting the determinant of lambda I minus a to 0, we get the equation lambda squared plus 2 lambda minus 3 equals 0. Factoring this gives us lambda minus 1 times lambda plus 3 equals 0. The eigenvalues are lambda 1 equals 1 and lambda 2 equals negative 3. Now let's find the eigenvector corresponding to the first eigenvalue, lambda 1 equals 1. We substitute lambda equals 1 into our eigenvector equation. Let's call our eigenvector x equals a, b. This becomes the matrix equation. Negative 1, negative 3, negative 1, negative 3 times the vector ab equals the 0 vector. This matrix equation is equivalent to a system of two linear equations. The first equation is negative a minus 3b equals 0. The second equation is negative a plus 3b equals 0. Notice that these two equations are scalar multiples of each other, as we expected. The second equation is just negative 1 times the first. Both equations simplify to a equals negative 3b. To find an eigenvector, we can choose any non-zero value for one of the variables. Let's choose b equals t, where t is a scalar. If b equals t, then a must equal negative 3t. Our eigenvector x is therefore negative 3t, t. For simplicity, we typically choose a value for t that gives the simplest integer components. Let's choose t equals 1. So the eigenvector corresponding to the eigenvalue 1 is negative 3, 1. Again, any scalar multiple of this vector is also a valid eigenvector for lambda equals 1. Now let's repeat the process for the second eigenvalue. Lambda 2 equals negative 3. We substitute lambda equals negative 3 into the eigenvector equation. This gives us the matrix equation. Negative 3, negative 3, negative 1 times a, b equals the 0 vector. This system of equations simplifies to negative 3a minus 3b equals 0, or equivalently, a equals negative b. If we let b equal a scalar t, then a must be negative t. The eigenvector x is negative t, t. Choosing t equals 1, we get the eigenvector x2 equals negative 1, 1, which corresponds to the eigenvalue negative 3. We have now successfully found both the eigenvalues and their corresponding eigenvectors. We have completed our second objective. This process is fundamental to all the applications we will explore next. Let's explore eigenvectors for the cases of repeated and complex eigenvalues. This covers our next objective. First, for a repeated eigenvalue. Recall our matrix A equals negative 3, negative 1, 1, negative 1, 1. We found it has a single repeated eigenvalue lambda equals negative 2. For a 2 by 2 matrix, this often leads to only one linearly independent eigenvector. We solve the eigenvector equation for lambda equals negative 2. This gives the matrix negative 1, 1, negative 1, 1 times x equals 0. This system simplifies to negative a minus b equals 0, or a equals negative b. Letting b equal t, we get the eigenvector negative t. T. There is only one direction for the eigenvectors here. Now for complex eigenvalues. This process is identical, but the arithmetic involves complex numbers. Recall our matrix A equals 2, 5, negative 1, 0. We found its eigenvalues are the complex conjugate pair 1 plus 2i and 1 minus 2i. Let's find the eigenvector for lambda 1 equals 1 plus 2i. Substituting this into our equation gives the matrix negative 1 plus 2i, negative 5, 1, 1 plus 2i times x equals 0. Let's use the second row, as it looks simpler. The equation is a plus 1 plus 2i times b equals 0. So a equals negative 1 plus 2i times b. Letting b equal t, the eigenvector is negative 1 plus 2i t. Choosing t equals 1 gives us negative 1 minus 2i, 1. For the other eigenvalue, lambda 2 equals 1 minus 2i, we would find a corresponding eigenvector of negative 1 plus 2i, 1. In this case, the eigenvectors are also complex conjugates of each other. We have now seen how to find eigenvectors for all three types of eigenvalues we encounter. This is a complete solution to our second objective. Our next topic is matrix diagonalization. This is a powerful technique that will enable us to do much more with matrices, especially calculating powers. The goal is to find a way to transform a matrix A into a simpler form. The simplest form a matrix can take is a diagonal matrix. A 2x2 diagonal matrix has non-zero elements only on its main diagonal. A diagonal matrix is very easy to work with. A square matrix A is said to be diagonalizable if there exists an invertible matrix P, such that the product P inverse times A times P equals a diagonal matrix D. The key insight for diagonalization comes from our work with eigenvalues and eigenvectors. If a 2x2 matrix A has two distinct eigenvalues, lambda 1 and lambda 2, with corresponding eigenvectors x1 and x2, then we can form the diagonalizing matrix P. The matrix P is formed by placing the eigenvectors side by side as its columns. The order matters. The first eigenvector corresponds to the first eigenvalue, and the resulting diagonal matrix D will have the eigenvalues of A on its main diagonal. This means D is the diagonal matrix consisting of the eigenvalues corresponding to the eigenvectors in P. Let's work through an example to verify this process. Consider the matrix A equals 0, 3, 1, negative 2. We already found its eigenvalues to be lambda 1 equals 1 and lambda 2 equals negative 3, with corresponding eigenvectors x1 equals 3, 1, and x2 equals negative 1, 1. Now we construct our diagonalizing matrix P. We place x1 in the first column and x2 in the second column to form P. Next, we need the inverse of P. The determinant of P is 3 times 1 minus 1 times negative 1, which is 4. The inverse of P is 1 over 4 times the matrix with columns 1, negative 1, and 1, 3. Finally, we compute the product P inverse times A times P. We multiply the three matrices together. The order is important. First, we multiply P inverse by A. This gives us 1 over 4 times the matrix 1, 1, negative 1, 3. Now we multiply this result by P. This product results in 1 over 4 times the matrix 4, 0, 0, negative 12. Dividing by 4, we get the diagonal matrix 1, 0, 0, negative 3. As you can see, the elements on the diagonal are exactly the eigenvalues of A, lambda 1, and lambda 2. We have successfully diagonalized A. This concludes our objective on diagonalization. We have seen how to construct the diagonalizing matrix P and how the process results in a diagonal matrix with the eigenvalues on the diagonal. Our final main objective is to use diagonalization to calculate matrix powers. Finding a matrix raised to a large power can be a very tedious calculation, but diagonalization makes it surprisingly simple. Let's start with our diagonalization equation. We know that P inverse times A times P equals the diagonal matrix D, which contains the eigenvalues. We want to find an expression for A in terms of P, D, and P inverse. To do this, we can undo the diagonalization. By pre-multiplying both sides by P and post-multiplying by P inverse, the P's and P inverses on the right cancel out, because P times P inverse equals the identity matrix. This leaves us with A equals PD P inverse. So we have a new way to write our matrix A, PDP inverse. Now let's see how this helps us find A squared. A squared is A times A. We substitute our new expression for A. Notice the term P, inverse times P in the middle. P inverse times P equals the identity matrix, which doesn't change anything in matrix multiplication. So A squared simplifies to P, dp inverse, or PD squared P inverse. You can probably see a pattern emerging. What do you think a to the power of n will be? That's right, it's pd to the power of np inverse. The task of raising a to the power of n has been transformed into raising the much simpler diagonal matrix d to the power of n. So how do you find the power of a diagonal matrix? It's incredibly easy. To find d to the power of n, you simply raise each eigenvalue on the diagonal to the power of n. D cubed, for example, would be lambda 1 cubed and lambda 2 cubed on the diagonal. Let's put this into practice with our running example. Let's use diagonalization to find a to the power of 6, where a is the matrix from before. We have everything we need from our previous calculations. We have the diagonalizing matrix P, its inverse P inverse, and the diagonal matrix D, which holds the eigenvalues 1 and 3. Now we can write down our formula for a to the 6. A to the 6 equals P times D to the 6 times P inverse. First, we calculate D to the 6. It's the diagonal matrix with 1 to the 6 and negative 3 to the 6 on the diagonal. Since 3 is raised to an even power, the result is 3 to the 6, which is 729. Now we substitute this back into our expression for a to the 6. This is 1 over 4 times P times D to the 6 times the other P inverse matrix. Let's perform the multiplication. First, P times D to the 6 gives the matrix 3, 729, 1, 729. Now we multiply that by the last matrix and the scalar 1 over 4. This gives 1 over 4 times the matrix 732, 2, 184, 728, 2190. Dividing each entry by 4, we arrive at our final answer. A to the 6 equals 183, negative 546, negative 182, 547. We have successfully found a high power of a without needing to do 6 matrix multiplications. Diagonalization can also be used to define fractional or negative powers of a matrix, as long as the matrix is diagonalizable. The logic is the same. To find the square root of a, for example, we write it as a to the power of 1/2. Using our formula, this is p times d to the 1/2 times p inverse. And d to the 1/2 is just the diagonal matrix with the square roots of the eigenvalues on the diagonal. For this to work, the eigenvalues must be real and non-negative. If any eigenvalue were negative, its square root would be imaginary, and if it were 0, the diagonal matrix D would not be invertible, which would break the formula. Similarly, we can define negative powers. A inverse, or a to the negative 1, is p times d inverse times p inverse. D inverse is simply the diagonal matrix with the reciprocals of the eigenvalues on the diagonal, provided they are not 0. This demonstrates the versatility of diagonalization beyond finding integer powers. It's a foundational concept that extends our ability to manipulate matrices. Let's summarize what we have learned today. We started with the weather model to provide context for a Markov process, which we can solve using eigenvalues and eigenvectors. We defined an eigenvector x as a vector that is only scaled, not changed in direction, by a matrix A. The scaling factor is the eigenvalue lambda. To find the eigenvalues, we solve the characteristic equation. This is always the first step. For each eigenvalue, we substitute it back into the eigenvector equation to find the corresponding eigenvectors. If a matrix A is diagonalizable with distinct eigenvalues, we can write it in this form. P is the matrix of eigenvectors, and D is the diagonal matrix of eigenvalues. Diagonalization allows us to express A in a simpler basis. Finally, we saw that this is incredibly useful for finding matrix powers, A to the n, by simply raising the eigenvalues to the power of n. To solidify your understanding, let's work through 5 IB-style practice questions. I encourage you to pause the video after each question is displayed and attempt to solve it on your own before watching the solution. Question 1 asks you to find both the characteristic polynomial and the eigenvalues for the matrix A equals 1, 4, 1, negative 2. Remember, the characteristic polynomial is dt lambda y minus a, and the eigenvalues are the roots of that polynomial. Question 1. Find the characteristic polynomial and the eigenvalues for a equals 1, 4, 1, negative 2. Pause the video now to try this yourself. Welcome back. Let's look at the solution to question 1. First, we find the characteristic polynomial by calculating the determinant of lambda I minus a. This is the determinant of the matrix with entries lambda minus 1, negative 4, negative 1, and lambda plus 2. The determinant is lambda minus 1 times lambda plus 2 minus 4. Expanding this gives lambda squared plus lambda minus 2 minus 4, which simplifies to lambda squared plus lambda minus 6. So the characteristic polynomial is lambda squared plus lambda minus 6. To find the eigenvalues, we solve the characteristic equation by setting the polynomial to 0. We need to find the roots of lambda squared plus lambda minus 6 equals 0. This quadratic can be factored. It factors into lambda plus 3 times lambda minus 2 equals 0. Therefore, the eigenvalues are lambda equals -3 and lambda equals 2. You have now found the characteristic polynomial and eigenvalues for this matrix. Now for question 2. This question asks you to find both eigenvalues and their corresponding eigenvectors. The matrix is B equals 5, 6, -1, -1. Pause the video and work out the eigenvalues and the two eigenvectors. Let's review the solution for question 2. This is a multi-step problem. First, we find the eigenvalues by solving the characteristic equation. The determinant of lambda I minus b gives us lambda squared minus 4 lambda plus 1 equals 0. We must use the quadratic formula to find the roots, which are 2 plus root 3 and 2 minus root 3. Now we find the eigenvector for the first eigenvalue, lambda 1 equals 2 plus root 3. We solve lambda 1 I minus bx equals 0. The second row gives the equation a minus 3 plus root 3 top dot equals 0, so a equals 3 plus root 3 top d a. Choosing b equals 1, the eigenvector is 3 plus root 3, 1. Next, for the second eigenvalue, lambda 2 equals 2 minus root 3. Solving lambda 2 I minus bx equals 0, we find that a equals 3 minus root 3 bashi b. With b equals 1, the eigenvector is 3 minus root 3, 1. So we have found the eigenvalues 2 plus or minus root 3 and their corresponding eigenvectors. Well done if you solved this one correctly. Question 3 brings back the complex eigenvalues. Find the eigenvalues and eigenvectors of c equals -1, -1, -4, 2. Take your time to work through the complex arithmetic. Here is the solution to question 3. First, the eigenvalues. The characteristic equation is lambda squared minus lambda plus 6 equals 0. The quadratic formula gives us the complex eigenvalues 1 over 2 plus or minus I times the square root of 23 over 2. Note these are complex conjugates. Next, let's find the eigenvector for lambda 1 equals 1/2 plus I squared 23, 2. Solving the equation for this eigenvalue, we get the relationship a equals -1/2 plus I squared 23, 2b. Letting b equal 1, the eigenvector is -1/2 plus I squared 23, 2, 1. For the conjugate eigenvalue, we find the conjugate eigenvector. The eigenvector for the conjugate eigenvalue is -1/2 minus I squared 23, 2, 1. The key takeaway is that the same process works, just with complex numbers. Question 4 asks us to prove a property of diagonal matrices. Show that the eigenvalues of the diagonal matrix D, with entries lambda 1 and lambda 2 on the diagonal, are simply lambda 1 and lambda 2. Pause the video and see if you can prove this using our standard method. Let's prove the property that the eigenvalues of a diagonal matrix are its diagonal entries. We start with the characteristic equation det mu I minus d equals 0. We use mu for the eigenvalues of d to avoid confusion with the lambdas already on the diagonal. The determinant we need to calculate is mu minus lambda 1, 0, 0, mu minus lambda 2. Calculating the determinant is straightforward for a diagonal matrix. It's just the product of the diagonal entries. This gives mu minus lambda 1 times mu minus lambda 2 equals 0. The solutions mu are clearly lambda 1 and lambda 2. This proves that the eigenvalues of a diagonal matrix are simply its diagonal entries. This is a very useful property. Finally, question 5 is a multi-part problem that brings together diagonalization and matrix powers. The matrix A is 3, 4, 5, 2. First, find its eigenvalues and eigenvectors. Second, find the diagonalizing matrix P and verify that P inverse AP is diagonal. Third, find an expression for a to the power of n. Fourth, and most impressively, find the exact matrix A to the power of 13. Good luck! Let's solve the comprehensive final problem. Part A, finding eigenvalues and eigenvectors. The characteristic equation is lambda squared minus 5 lambda minus 14 equals 0. This factors into lambda minus 7 times lambda plus 2 equals 0, giving eigenvalues lambda 1 equals 7 and lambda 2 equals negative 2. The eigenvectors are x1 equals 1, 1, and x2 equals 4, negative 5. Part B, verification. The diagonalizing matrix P is formed by the eigenvectors 1, 4, 1, negative 5. Its inverse is negative 1 over 9 times the matrix negative 5, negative 4, negative 1, 1. Calculating the product P inverse AP gives us the diagonal matrix 7, 0, 0, negative 2. This verifies that we have diagonalized the matrix A. Part C. General expression for A to the power of n. The general formula is A to the n equals P times D to the n times P inverse. D to the n is the diagonal matrix with the eigenvalues to the power of n. Part D. Finding P inverse A to the 13p. Notice the structure of the expression we need to find. It's the same form as the diagonalization itself. Therefore, the result will be the diagonal matrix of the eigenvalues raised to the power of 13. This gives us 7 to the 13, 0, 0, negative 2 to the 13. This demonstrates a powerful simplification. Once a matrix is diagonalized, any expression of the form P inverse A to the Kp is simply the diagonal matrix of the eigenvalues to the power of K. This highlights the true power of diagonalization. We have now covered the core concepts of eigenvalues, eigenvectors, diagonalization, and their application to matrix powers. We started with the weather model, a Markov process, to illustrate the practical relevance of finding a steady state using these tools. You have learned how to find eigenvalues by solving the characteristic equation, date lambda I minus a equals 0, and how to find corresponding eigenvectors by solving open paren lambda I minus a close paren x equals 0. We have seen that diagonalization, which transforms a matrix A into a diagonal matrix D via the formula D equals P, inverse times A times P, where P is the matrix of eigenvectors, is a key technique. And finally, you are now able to compute high powers of a matrix efficiently using the formula A to the n equals P times D to the n times P inverse. Mastery of these topics is essential for success in the IB Mathematics AI/HL course. Keep practicing with more questions from your textbook and past papers. If you require more in-depth support, please remember that DAR Tutors offers expert tuition. Thank you for watching.